Welcome all of you. Probably this is the last class of this course. I don't know, maybe still lot more things to cover. Possibly I may come back with short one or two classes, maybe after some time. But as far as I am concerned, as for the solid state NMR, lot more to discuss. I have not even brought in two-dimensional NMR in solids. There are many things which we can discuss. If I start that, it will take another 10 hours to discuss. There is no time because the time is a course restricted to only 30 hours. I cannot go in depth and discuss everything. So solid state NMR will finish and this could be the last class. Just to give you the information about some of the one or two techniques, I will come back later, maybe one or two extra classes. So as last class we discussed about solid state NMR, especially last couple of classes we have been discussing. We discussed a lot about magic angle spinning, Wah-Wah techniques, averaging in the spin space, physical space, varieties of things. Last class we discussed extensively about the CP mechanism, cross polarization, where you can transfer the magnetization from abundant spins to rare spins. This mechanism involves heteronuclear dipolar interaction. Dipolar coupling is essential, and we consider by understanding using thermodynamics approach. You can consider proton and carbon 13 are two temperature thermal baths, and we by the spin temperature concepts we understood carbon 13 in the rotating frame is extremely hot, whereas proton is very cold, extremely cold. At lattice temperature protons will be at 300 K in the rotating frame, in the doubly rotating frame it is at 0.05 K. So very small, and because it is so cold, carbon 13 because of lack of magnetization, assuming they will be in the saturated state, they are very hot. Now somehow if I bring them into contact, which is not possible in the lattice temperature at the room temperature, because if we increase the magnetic field to 1, it's in linearly it changes with others also. Whereas in the rotating frame there is a possibility I can tune the RF power of one of them so that the energy level between these two become equal. This condition is called Hartmann-Hahn condition, which is nothing but the gamma of proton into B1 of proton is equal to gamma of carbon 13 into B1 of carbon 13. It is carbon 13, it could be any dilute spin. This is, if you match this condition called Hartmann-Hahn condition, then spins lose their identity. Both the energy levels of proton and carbon are similar, are identical, in which case spins can simply transfer their magnetization. Because of the thermal and and the thermodynamics we understood, protons are at very low temperature and carbon 13 is very hot. There is a transfer of magnetization between proton to carbon 13. So there is enormous gain in the signal intensity, and of course we discuss a lot about T1 rho and everything, how the initially its signal builds up, and then if you wait for a long time it start decaying because of spin T1 rho. So you have to optimize the mixing time accordingly. And in the last class we also saw the enhanced intensity for one of the silicon spectrum. So we will start with that today and see how we are going to see this. This is silicon NMR which I showed last class. This is with only magic angle spinning, no cross polarization. With cross polarization magic angle spinning, you see nearly 5 times enhancement of the signal intensity. This is the biggest advantage of cross polarization. So if for any dilute spin, if they contain protons or any other abundant spin like fluorine, you can do the polarization transfer from one spin to other spin, especially from abundant spin to dilute spin. Okay, now just for comparison, I also showed this histidine spectrum, alanine histidine powder, and we saw that there is an enormous gain in the signal intensity by doing the cross polarization here. Here it took lot of time, 2 hours and 15 minutes, but with CP we took only 8 minutes. So there is a gain in the instrument signal to noise ratio, and 45 times experimental time more here, it reduced here. So this is what I wanted to show you, how the signal intensity and the resolution can be compared for different experiments you do. Consider a powder like this, sample like this, which is in a solid form. Solid, it is like a powder or whatever it is. Take the spectrum of this carbon 13 spectrum under solution condition. That means you don't do anything, simply put the sample in a spectrometer and collect the signal, and you don't see anything here. Broad hump, if you enlarge intensity vertically, you may see a broad hump. But whereas let us say we do the decoupling slowly, low power, you see some profile started coming up. With high power decoupling, something more happened, more resolution is there. Now simultaneously with high power decoupling, you do magic angle spinning and also cross polarization simultaneously. All the three you can do. You can do cross polarization, magic angle spinning and high power decoupling. Look at it, how sharp lens you are going to get. And this is the spectrum in solution state. Of course, there is no comparison between the resolution between this and this, and also you see sometimes you get more peaks than here, this here, for varieties of reasons. There could be spinning sidebands, or it could be different polymorphism, different structure in the solid state compared to solution state, varieties of reason. But nevertheless, you can get sharp peaks with all the states combined together. Okay, this is what it is. This is for the solid, low power decoupling, high power decoupling, with magic angle, and this is the same sample dissolved in the solvent CaDCl3. So look at this for another spectra like this. These are the experiments on glycine molecule. This is the spectrum. Look at this one. This is a static, no cross polarization and no decoupling at all. Here this is again a static sample, no cross polarization, but there is a decoupling. So because of decoupling you can see there is a resolution already. You have already broken some of the heteronuclear dipolar coupling. This is static cross polarization with decoupling. So then what is happening is you already enhance the signal intensity. Now this is a situation, cross polarization along with magic angle spinning, of course, and also decoupling, and look at it, there is a rotation speed is only 1 kilohertz. So you get lots of sidebands, and then keep on increasing the spinning speed, 3 kilohertz sidebands gets reduced. As I told you, I have been telling again and again, the separation between two spinning sidebands correspond to the spinning frequency. Again it is a 5 kilohertz, and this is a typical experiment, what is called a TOS experiment. TOS means total suppression of the spinning sidebands. I will tell you if there is a time today how we can remove the spinning sideband so that you can get only isotropic chemical shield peaks in the solid state. So this is the effect of CP, decoupling and spinning speed on variety on the sample. Varieties of experiments you can do, and finally this is what you are interested to see. So now we have several sidebands. I told you several spinning sidebands. You can see if you are spinning at a slow speed, for example in this, look at this one, in this example here you can see lot of sidebands here, and these sidebands could be messy. So how do you eliminate it? There are several ways, several experiments you can do to suppress the spinning sidebands. You can do efficient cross polarization method. We understood the cross polarization by in a thermodynamic approach, how using spin temperature concept, but there are several ways to enhance the signal intensity because it is not easy. It depends upon several parameters, depends upon homonuclear dipolar coupling, spinning speed, heteronuclear dipolar coupling, varieties of parameters. Okay. So how do you make the efficient cross polarization? What are the methods for it that we can understand for applicable to all spinning speeds? And there is selectively I can recover anisotropic interactions while doing all these experiments together. Cross polarization, magic angle spinning and decoupling you can do. Simultaneously you can extract, get back anisotropic interactions. That is also possible. There are ways you can understand the spin dynamics, how the CP dynamics, how the cross polarization dynamics takes place, what is happening, how the polarization transfer takes place. All those things can be understood. Now based on these things, number of 1 and 2 dimensional experiments have been designed in the solid state also. In the solid state NMR also, varieties of NMR experiments have been designed, and now we can obtain all the NMR, various NMR parameters, like selectively I can get chemical shift anisotropy, selectively I can get heteronuclear dipolar coupling, selectively I can get information about homonuclear dipolar couplings, or I can remove heteronuclear dipolar coupling CSA, and I can get only sharp peaks in carbon 13 and get chemical shifts. All these things are possible. Varieties of experiments can be designed. There are number of 2D and 3D experiments are there in solid state to derive the spectral information. Like we have umpteen number of pulse sequences, umpteen number of 2-dimensional experiments in solution state, 2 or 3D, 4D. Similarly, we have 2D, 3D experiments. Number of possible number of experiments are there. We can derive information in solid state also. Now, with the available time, we will not discuss many things possibly, but I will try to discuss today something about suppression of the spinning sidebands. This normally you come across. See, in all laboratories, you may not have the spectrometer facility to spin at 70 kilowatts or 80 kilowatts like that. Generally, you have spectrometers to spin at 5 kilowatts, 10 kilowatts or like of that order. Still, you may get lots of spinning sidebands in some exotic nuclei. For example, if you look for the silicon or aluminum or carbon, varieties of nuclei, you may get a lot of spinning sidebands. But you do not want to get spinning sidebands. You want to erase this, remove this spinning sideband, get only isotropic chemical shifts. Remember, I told you also last time. If you do a 2 or 3 spinning speeds, what will happen to the central band, central frequency corresponding to the isotropic chemical shift? That will not change the spinning frequency. It remains same. Whereas sidebands start moving away. That is what happens. So, we can efficiently suppress the sidebands. We do not have to do 2 or 3 such experiments. Then we can get only peaks pertaining to isotropic chemical shift in the solid state. There are several experiments like that. I will discuss only 2 or 3 of them. For example, one is called the VS MOS. VS MOS means variable spinning magic angle spinning. You can vary the spinning while vary the spinning speed while you are doing the magic angle spinning. It means I put the rotor here at magic angle and start rotating. Simultaneously, when I am acquiring, each time when I have acquired the signal, every time, every accumulation, I can keep on changing the speed. It is a little difficult task, challenging task, but it can still be done. I can vary the spinning speed while doing magic angle spinning each time while acquiring the signal. This is called variable spinning, magic angle spinning. Okay. And also we have rotor synchronization. I can synchronize the rotor in such a way spinning sidebands can be eliminated. If rotor keeps on rotating, okay, and I will see that for exactly after one rotation I correct the signal. Then in between it can have the powder pattern, a half rotation it will come like that, next half rotation it will get averaged out. So in one full rotation if I go and acquire the signal, wait for it to go one more rotation, acquire the signal. I can synchronize the acquisition with respect to rotor speed. While spinning this sample at the rotation speed, I can synchronize the data acquisition. This is called rotor synchronization that can also remove spinning sidebands. Also they are using a pulse sequence experiment by 4 pulse or 5 pulse experiment. This is called the total sideband suppression. We can adapt this and do this experiment. We can remove the sidebands completely. So these are all the things which can be adapted. Okay. So look at this one. Variable spinning, magic angle spinning is one simple experiment. Okay. This is taken from the paper Chemical Physics Letter 1996. This is the bromine 17 in NMR spectrum of potassium bromide. Look at this one. As I told you, when you use potassium bromide, look for bromine 17 in NMR. We tune the magic angle to see that you get maximum number of spinning sidebands. That is what we have to do to adjust the magic angle very precisely. So now you have a lot of sidebands here. Okay, in the case of bromine, you know this is the only central peak, this is the only one peak I know. But in some other cases, what you will do? In some other nuclei like carbon 13 with several carbons present, each may have a different CSA and each may have a different powder pattern and then different spinning sidebands. In which case what you will do? They will all overlap. So what to do is better to remove spinning sidebands. What you will do is we acquire signal at every time when you acquire we vary the spinning speed. For example, once I acquire the signal and this is the spinning speed I get, spinning sideband. Second time I will acquire, what will happen to the central band? That remains same. This gets added up, whereas next time I get the sideband like at different place because the spinning speed is different. Again I will acquire once more, I change the speed, central band again added up, this will move away. So like this, every time I keep changing the spinning speed, keep acquiring the signal. Then central band keeps adding up and side bands keep on moving away. So if you acquire for a long duration, because of signal averaging, this will grow and all the side bands get suppressed. Very nice idea, fantastic idea. This is called variable spinning, magic angle spinning. If you do that, look at it, we can get only central band, chemical shift to the isotropic frequency, all these things are removed, no side bands, they are completely removed. And this is in a complicated spin system. See, for example, an amino acid tyrosine, CP mass spectrum of it, look at it, there are so many side bands here. How do you identify the side band now? How do you know which are your peaks? For example, this could be side band. If you look at it, this may be exactly equal to this, and similarly you can see another side band at equidistance here. But they are all overlapped. Side bands and central bands, everything are overlapped here. How do you identify? Okay, you can do at another spinning speed. It may so happen when you do another speed, it may overlap with the isotropic peak somewhere here or here. So you may have to do 2, 3 speeds or 4 speeds to identify completely all the side bands and distinguish them from the isotropic peaks. On the other hand, do this Vs mass. In one experiment, while acquiring the data, the spinning speed is varied from 2000 to 4000 hertz. At every time when you acquire, it is speed is changed by 50 hertz. Fantastic. Look at it. These are all the side bands. They are all removed here. Here also side bands removed. Only central bands here. These are the 2 peaks which are central band. Okay, and these are the peaks. They are all retained. These 2 are retained. All other peaks practically are spinning side band. And over the period when you acquire this thing as a function of various spinning speed, then you are removing these things and you are retaining only isotropic peak. This is what is happening, and you see you get only isotropic peaks here. Second method is called the rotary echo. This is what I said, rotor synchronization. While spinning is going on, I can synchronize with the spinning, I can acquire the signal. Every time it goes for one rotation, correct the signal like that. Okay. So, for example, how it happens is like this. We know we discussed about the rotary echo. Rotary echo comes exactly at the spinning speeds. When the rotor starts here, let us say this is the marker here, this side. When it goes, rotates, comes by exactly to the same place where it started, you are going to see an echo pattern here. This is called a rotary echo. And now it keeps going like this as you keep on acquiring the FID, and it decays also with time. But in between what happens? If you consider for half the rotor time, let us say this is the time at which this is a marker is there, the rotor is in this position. Now you keep rotating, half the rotor time it has come, this marker has gone to opposite side. Now continue speed further, come back for half another speed of rotation. Now marker come back to the same place. Fantastic. Now just for one rotation, it started from here and came back to the same place. In between it goes to the powder pattern for half the rotor period, and then again goes back and averages out this powder pattern within one rotor period. So what I will do is, I do not acquire the signal in between. I will acquire the signal at the intervals exactly on one rotation period. I synchronize my acquisition at the rotor speed. Okay. Then what will happen? I collect the signal like this, like a rotary echo. That is what it is. So during the sample rotation, the crystallite orientation keeps on changing with their orientation with respect to magnetic field. But remember, as I said, after one complete rotation, they come back to the same orientation, same position where we started with. So that is what we do. We acquire a signal exactly at the integral multipole of the spinning frequency. You remove the side bands. You get only isotropic chemical shifts. So powder pattern which you come at half the rotor period, for the remaining half it will disappear, it will get nullified, and you get only isotropic chemical shifts if you acquire signal exactly at the integral multiples of the spinning rotor speed. This is an example to show, simple experiment. Look at it, this is for some sample, do not worry. This is spinning at 1.25 kilohertz. You see how these are all called rotary echoes. So now keep on acquiring the FID like this, exactly on the top you have a decaying signal. Do the Fourier transformation of it by collecting the signal exactly at the top of it. you get a Sharpie. Where are the sidebands? They disappeared because you synchronize your acquisition with the spinning speed. Okay? If you acquire the data at the top of the rotational echoes, you will remove the spinning side bands. You are going to get only isotropic chemical shifts. This is a simple experiment called rotor synchronization. All right. We will go to the another method. Another method is called total suppression of the spinning side bands, called TOSS experiment. TOSS means total suppression of the spinning side bands. This is an experiment which you do by playing with the spin dynamics. What we do, this is a famous paper by Dixon's paper in the 82, he has published in JMR. You will apply series of pulses, sometimes 4 pulse sequence Dixon's, 5 pulse sequences are there at different fractions of the rotor period. There is one rotor period I told you, started like this, go back and come to the same place is one rotor period. During this one rotor period, at different fractions of the rotor period, we apply RF pulses. And it is manipulated in such a way, what happens if you do, the orientation of the crystal changes with the magnetic field as the sample is rotated. But what happens when you acquire the signal at different RF pulses you apply for one rotation, the magnetization is X, it goes back like this and comes back to the same place. It is tuned in such a way. The central band comes back, start from this place, comes back to the same place where it started after one rotation. Whereas side bands, they keep on dispersing. Okay? They will not come back to the same place. They like complete dispersion in the XY plane takes place, like what you saw in the XY plane. So there is a dispersion of the signal, this thing, sideband magnetization, and you are not going to collect that at all. You are collecting only central band signal by applying a series of RF pulses. Central band is made to come back to the same place, central band magnetization. After one rotation, it will be at the starting point where it started. Whereas side bands completely get nullified because of dispersion like this. Okay. And central band precedes at isotropic frequency, side bands at n omega r frequency. Okay. Now, this transverse component can be resolved into center band and sideband magnetization for each crystallite. At the end of the sequence, it so happens central band magnetization adds up constructively, sideband magnetization have random phases, they will add destructively, it average out to 0. That is what happens. Central band magnetization adds up constructively at the end of the Dixon sequence, whereas sideband magnetization gets nullified, they average out to 0. Okay. This is a simple experiment to show 50.3 megahertz carbon 13 spectra of glycine powder at a rotor spinning frequency of 1 kilohertz approximately, and this is a normal CP-MOS spectrum, okay, of glycine. Look at it, this is for the C alpha CO carbon, this is the CA3 carbon. Look at this one, how many sidebands are here? Lot of sidebands are there. Now, if you do only one experiment, if I do not know where is it coming, where the isotropic chemical shift comes, how do you say which is the center band, which is the isotropic chemical shift? You cannot say so easily. So, what we do is, we do the TOSS experiment, total suppression of the spinning side bands by using this Dixon method. Then all the side bands disappear, only central band will be retained. Side bands add destructively. Central bands keeps on adding up constructively, that is retained. This is the TOSS comparison of glycine powder. It can efficiently remove side bands in a very complex spectrum like this. Look at this, a complex molecule carbon 13 CP-MOS. This is with TOSS, this is without TOSS. See, without TOSS, so many side bands are there here. Here now with TOSS, all the side bands are removed, no side bands. This is an advantage. Okay. So, now quickly I will introduce few terms, there is no time to go into the details. Plus, let us see what another 5-10 minutes I will give you some ideas about high speed cross polarization. This cross polarization transfer depends upon static heteronuclear dipolar interaction. Okay. 13C signal intensity as a function of RF mismatch, you can plot it. For a static sample, It is a broad powder sample, no problem. You can keep on finding where is the say RF power and see where you can get the CP matching, cross polarization, Hartmann matching where you are going to see. For spinning samples, when homonuclear interaction is sufficiently larger than omega r, polarization transfer is effective. That is what I said. It depends upon the interaction strengths also. On the other hand, for spinning speed comparable to proton-proton homonuclear or heteronuclear dipolar coupling, especially in the sample when omega r is larger than the homonuclear interactions, matching of the profile breaks into side bands. Remember, this is different from spinning side bands. These are called CP side bands. To make you understand, I will tell you what we go ahead further. We achieve the Hartmann condition by this. What you can do is keep the power on one of the channels, proton or carbon 13, and keep on varying the power level of the other one until you get the maximum signal, okay, and start plotting it. This is the way you adjust the Hartmann. This is the Hartmann mismatch condition, this is Hartmann match condition. Look, beautiful FID you are seeing. When the Hartmann is mismatched, there is no signal at all. This is the normal conventional decomposition CP sequence which I said. So now we can carry out two experiments. Keep a static sample, that means no spinning, put a sample in a magnetic field, keep RF power of one of them like carbon or proton constant, and let us say I keep carbon RF this thing constant, keep on varying the RF power of the proton at regular intervals. I am not spinning the sample yet. Each time measure the intensity of the peak. One of the peaks you take as a standard, keep on measuring the intensity. Repeat the experiment with the spinning speed. Okay. Now plot the graph of the intensity of the peak as a function of the RF power. You do this experiment. Now this is for the static sample. You have collected the data at different RF powers. For the carbon 13 RF power, see this. Now what is going to happen is Hartmann match when it is RF power of the omega I channel and proton, and then for the S channel when they are equal, Hartmann matching is there. In the static sample you see, you can get the matching at any of these places. So what is happening is, now Hartmann matching is there between this and this, and you keep on measuring it. This is a broad profile. Anywhere you put the CP condition, you get the signal. Very beautiful. Now the same time you spin the sample. See, when you are here you get the signal, when you are here you get the maximum signal. When you are here you do not get the maximum signal. It is 0 or less signal, less intensity. So again you plot the intensity, you see it looks like a sideband, but they are not spinning sideband. These are called CP sidebands. And now that means in a situation like this, for example adamantine, which is a plastic crystal, natural averaging has removed the dipolar interactions. So rapid isotropic motion is the HH dipolar couplings are small. This is attenuating the intramolecular dipolar interactions. So now CP profile for this is very bad, and if you start doing the experiment, there is a Hartmann mismatch. So look at another example of the carbon 13 of cadmium 113 of this molecule. Again in the static case, a broad hump, you are going to get matching profile over a wide range, whereas here matching profile breaks down into side bands. It was spinning at a 2.5 kilohertz. Now this is again because of weak dipolar interaction in this molecule due to isotropic dilution. On the other hand, look at the carbon 13 signal amplitude of the polyethylene, another molecule. Again, this is a static sample. Look at it, intensity keep on varying. At this place, if you are sitting, you are sure to get the maximum signal intensity. If you are sitting here after the RF power, then very low intensity. Okay, you understand how you can measure this? Set the CP condition, keep on varying the RF power of one of them in the static case, keep on measuring the intensity and draw a plot. Identical condition to the magic angle spinning, you will see you will have a different profile. It breaks into spinning sidebands. So we will not worry about it. Now CP signal obtained at the top of the sidebands, you get a signal, and in between you do not get the signal at all. So spinning does not eliminate the polarization transfer. Remember, spinning is not eliminating the polarization transfer, but CP optimization is difficult in regular interval multiples of that CP sidebands. At the top of the CP sideband you get the signal, anywhere in between intensity is lower. So this is problem you have to overcome by special pulse sequences, and there are number of methods available for this. For example, variable amplitude cross polarization, ramp amplitude CP, ramp speed spinning, rotor synchronized amplitude modulation, simultaneous phase inversion, RF driven CP, and variable effective field CP. Lot of things are there. Several experiments are designed to overcome this, and especially when you have a dipolar coupling, this type of system can happen in some systems. In the homonuclear dipolar couplings are very small, because of the natural averaging you are going to get CP sidebands. CP adjustment is very difficult. In such cases you adopt any one of these methods, you are going to get fantastic comparison of the intensity. I will show you one example. Here the same CP condition here. Instead of RF power being equal, keep on varying the amplitude of the RF power, CP power here. In the case of proton, I don't make it uniform, I keep on varying the amplitude over the entire mixing cycle. For carbon 13 I don't do anything. Conventionally you do this and then start acquiring the signal. It overcomes the oscillatory behavior, and the CP sideband profile will be removed. And look at this one. This is what happens. If I take the 13th spectrum of different amino acid mixtures here, this is at 15 kilohertz, 11 kilohertz and 5 kilohertz spinning. And here you see the intensity. It is very difficult to match the intensity. Okay. Here also. Whereas, okay, 5 kilohertz is little better. But look at this one, 15 kilohertz. Here it is very bad. Now this is the speed, intensity of the peaks here. This is because here in this experiment VACP has been done here. Okay. Here this is with VACP, variable amplitude cross polarization. Here is a conventional CP. What it does is it will overcome the oscillatory behavior. Okay. And we can start discussing what various other pulse sequences, other experimental techniques which are adapted for this thing. So I don't think there is time to discuss all those things. And also I tell you, all these things experiments I was discussing only the one dimensional experiment, where we get sharp lines, we understood CP mechanism, what happens at the high speed spinning and low speed spinning, and why CP adjustment is difficult at high speed spinning, CP breaks into CP sidebands we discussed. And then we have overcome this method by varieties of pulse sequence design like VACP, variable amplitude, variable phase, all these experiments we have been designed so that CP efficiency transfer of magnetization is efficient. So we don't have time to discuss everything, but then the 2D experiments have been designed in such a way, all these techniques you can incorporate in the T1 dimension, the T2 dimension, and design the 2D experiment so that you can get the results. You can get the results what you want. That means you can also extract particular information of your choice. You can remove the interactions and correlation like our chemical shift correlation COSY and TOXY in the homonuclear protons in the solution state. Here also you can do carbon 13 correlation, but that is an experiment called RFDR. Similarly, I can design an experiment to get only proton dipolar couplings, proton homonuclear couplings. I can get only heteronuclear couplings. I can get only chemical shift anisotropy like that. I can remove the sidebands and I can get only isotopic in one direction. Other dimension I can incorporate TOS. So another dimension I can incorporation D-TOS I can do. All varieties of combination of pulse sequences are there. As I said, there is not much time since this is the last class. I have not discussed, but I wanted to give you an idea. Probably in the next course when there is an opportunity I will come back and discuss lot of the solid state NMR experiment for the benefit of those who want to specialize in NMR. So right now I am going to stop here. In the broad classifications of solid state NMR experiment I discussed, and I gave you idea of what is magic angle spinning. I gave you idea of about what is spin space averaging, what is a cross polarization, how the cross polarization works, and what happens at the low spinning speed, what happens at the high spinning speeds, and all those things we discussed. All of them are very important, very useful. So you understand these things. These are all important techniques. So possibly I don't know if I will see if time is available. Quickly I will come and give one or two simple 2D experiments in the case of solid. In fact, mind you, I have not even discussed DOSY. I have not discussed the pure shift experiments. I don't see the time is too short to discuss everything. I tried my level best to cover maximum. If I keep going at the rapid speed, then if following you may not be able to follow everything, and if I go rapidly. So it is the available time, it is impossible to cover everything. But if there is a time, I will come back and talk something about pure shift, and if possible in one class, 1 or 2 2D experiment of solids I will discuss. Let me see, I will think over it and come back. But as far as I am concerned today, our course is coming to an end. Please go back. This is, as I said, NMR is a big ocean. Whatever I have been discussing will be a tip of an iceberg. Lot more things are there to discuss. Each and every topic we discussed, one can discuss for hours and hours. A lot of developments are there. Several stalwarts in NMR have designed experiments. Every time they have improved upon the methodologies, we can understand all those things. So it is a big ocean. So with the ideas I have given, general principles, concepts, and type of experiments one can do, type of information you can derive. So you have got a basic knowledge, basic idea. Further improvement about your knowledge you can do by going into the literature and understand other recent developments. Thank you. I am going to stop here. Thank you very much.